Walking. Yeah, these Newton Institute clocks are a bit slow sometimes. So Professor Robert Buckingham from Cincinnati, he will talk to us on the universality of high-order Rogue waves.
All right, thank you. Thank you to the organizers, both of the program and of the workshop, for the invitation. It's been a pleasure, and thank you all for coming today. So I would like to show you a series of different results that we've had over the last few years, try to tie them together and pique your interest in what I think is a very promising area. So I'm going to be focusing on wave breaking, which Vera brought up at the very beginning of the first talk. And I'm going to give a little bit of background on wave breaking, which most of you are very familiar with, but then talk about how different scenarios you still see the same local behavior, and in particular a type of non-generic breaking that leads to rogue wave behavior. Okay. And so I'm going to argue that this is universal in the sense that it shows up in many different problems. And so I'm going to, for example problems, I'm going to run through 4 of them in this talk in more detail, and 2 of them will be addressed in other talks at this conference. So, okay. So to begin, we're looking at dispersive nonlinear wave equations. So picture you're all very familiar with. So I'm not actually going to be studying this type of wave breaking at all, but let's just start here. So you've got your KdV equation. Now I've chosen a parameter, a dispersive parameter here to be very, very small, 1/420. Okay, and so these are exact solutions of the KdV equation. And so as it moves, as your profile moves to the right, this is the time we're interested in. You're about to get the oscillations. Okay, and so it starts at this point. The derivative becomes too steep, right? And you've got too much energy there. You've got to shed this energy, and so it turns into this dispersive tail. So, okay. And so we're not interested in the dispersive shock wave that develops, but we're interested in just before this time when the oscillations start. Okay. So there was a very nice conjecture by Boris Dubrovin that not just for KdV is a good model equation for this, but for any Hamiltonian perturbation of a hyperbolic equation, that generically you're going to have at a breaking point, this gradient catastrophe point, that you're going to have your local behavior will be described by a certain function, and this function satisfies the second member of the Painleve-III hierarchy. Okay. And so this is a classical conjecture by now, and was proven, for example, by Claes and Grava in 2008 for Korteweg de Vries. So now, here is the type of wave breaking that I'm going to be starting with, at least, and then we'll tweak it. So you get something different with NLS. So here you start out with a smooth, we're looking at amplitudes here, so it's complex valued, but take the amplitude and start out with a nice smooth single hump solution, let it evolve, okay, and generically you're going to eventually have this focusing point for focusing NLS. In this case, we're starting with initial condition, but essentially a Gaussian, okay? with this phase here. And right, it's very clear that there's the nice smooth region, and then you get the well-known oscillatory region. And what we're interested in is not even the edge, which is another interesting question, but this, the very first point, okay, where the oscillations first start to appear. Okay. And Dubrovin also did some scaling analysis and conjectured that there was not just for NLS, but for any Hamiltonian PDE that commutes with the wave equation, that the generic behavior near a breaking point, well, he gave full details of what the solution should look like. I'm just going to say a little bit about it. Among other pieces of the description it involves the tree trunquet solution of the Painleve-III equation. Okay, so again, we see Painleve equations are coming up, and so we often see these Painleve equations at the boundaries between different regions in dispersive wave equations. So that's perhaps not unexpected. And so this is so on the right here, what we have is a plot that illustrates the poles of the tree trunquet solution. Okay, and so in general, solutions of we're looking at the complex plane here on the right-hand side. Okay, and so in general, the Painleve-III equation, it's got depends on a complex variable x. Okay, it's an ordinary differential equation, right? And so it's got poles in the complex plane. Solutions have poles. Generically, they might fill up the whole, most of the plane. However, there are special solutions known as trunquet solutions that don't have poles in a particular sector. And then the tree trunquet solutions are special trunquet solutions. They don't have poles in most of the plane, and they only have poles in a sector of 2 pi over 5. Okay, and so that the fact that the poles are actually confined to that region was recently proven by Costin and collaborators. And so what we've got on the left-hand side here is the same NLS picture we saw before. And so that's two real variables, right? And so we've got space and time. And so there's this, you can see it, right? There's clearly some sort of map between these two real variables and the one complex variable over here. And you see these little spikes inside the oscillatory region for NLS. And those spikes you can prove, as long as you're in a small dispersion limit, the location of those spikes are exactly the locations of the poles in the tree trunquet solution. So very, really a beautiful picture mathematically here. And this conjecture was proven by Marco and Alex in 2010 for NLS, and more recently for Sine-Gordon by Binging and Peter. So, okay, and so we'd expect, because the scattering problems are related for NLS and Sine-Gordon, we might expect we'd be able to use similar techniques to prove both these results. Okay, so that's the well-established background. And so what I'm going to look at is a non-generic case, right? So those conjectures were for the generic case. If I just start with initial data, right, and let it evolve, that's what you would expect to happen. But you can always fine-tune your initial data and try to make something else happen, right? And so here is one thing that seems to happen. A generic, non-generic behavior. So a non-generic behavior that seems to happen across a wide variety of contexts. So, okay, so I'm going to just for shorthand refer to these two types of focusing. The generic type I'm going to refer to as Painleve-I type breaking. Okay, that's where we get these this opening wedge of little bumps. Okay, and going to compare that to what I'll call Painleve-III type breaking because of a different equation that shows up in the description. Okay, and so as it says here, even though Painleve-I is expected to be generic, okay, we've got a particular type that we're going to focus on. Okay, all right, so let's look at a particular example. All right, and so I'm going to look at two different solutions of NLS. Okay, the first one is going to be the well-known Satsuma-Yajima initial condition. And so you know that the SETCH is the hyperbolic secant, is the soliton solution for focusing NLS. Okay, until you start to vary the dispersion parameter. Okay, and so if I change the dispersion parameter, then hyperbolic secant doesn't, it's no longer a soliton. Okay, just something else happens. But you can still compute the scattering data exactly. Okay, and so you can solve this problem. And even more interestingly, there's certain values of the dispersion parameter. There's an infinite sequence of dispersion parameters tending to 0 for which the solution is reflectionless. Okay, and so this gives you a nice playground of solutions to work with. So those all, so as epsilon as your dispersion parameter epsilon tends to 0, we're going to get Painleve-I type focusing. And then we're going to look at a second solution. And so Bob Jenkins will be talking much more about these Talanov pulses, some other classical solutions of the dispersionless NLS and relations to the NLS equation. And these are semicircle initial data, or one of the classes of Talanov solutions is semicircle initial data. Okay. So, and that will exhibit this Painleve-III types focusing. Okay. And so what I'm going to do is interpolate between the two with some exact solutions. Okay. And the way I'm going to do that is by using the idea of a semi-classical soliton ensembles. So let me just say a word about semi-classical soliton ensembles. So the idea is basically that if your scattering data if there's no radiation in the solution, if your scattering data has no reflection, and you just have poles in your Riemann-Hilbert problem, then you can solve, you can do the inverse scattering exactly. Okay. And so the idea is to take a solution that you're interested in studying and approximate it by a reflectionless solution. And this might be a good idea in certain asymptotic limits. In those cases, in many cases, you can actually prove that at least at the initial time, your approximation becomes better and better to the solution, to the function you're trying to study. Okay. So, right, then that's this idea here that the radiation isn't, at least in the small dispersion limit, radiation doesn't contribute. Okay. So, all right, so this last bit here says that if you have the discrete Riemann-Hilbert problem arising from this reflectionless problem, well, the price you pay is that as your dispersion parameter gets smaller and smaller, then you get more and more poles, okay? But you get a better and better approximation. And as long as n is still finite, the number of poles is finite, you can still solve solutions explicitly by linear algebra, so we can actually plot exact solutions. So that's our motivating example here. Okay, so the idea, we're going to start with this solution here, the setch, and you see a breaking region, right? So nice smooth going into an oscillatory region and standard setch. Now I'm going to interpolate to a square root function, to a semicircle function. Okay. And so on the left-hand side, okay, on each of these pictures, what you see is in blue, we see the function that we're approximating. Okay, that's the function that's given up here. That's the Cauchy data I'd like to approximate. In red, we have the semi-classical soliton ensemble. That's my actual Cauchy data. Okay, if I took n to be larger, then I would have more wiggles, but the deviation from the function I'm approximating would be smaller. Okay, but the picture on the right-hand side would look similar in many aspects. The smooth region would still be the same. The boundary would look pretty much the same. The boundary between the smooth region and the oscillatory region would stabilize, and the oscillations inside the oscillatory region would get faster. Okay. And so let's scan through these. Let's go back. So on the beginning, we have hyperbolic secant, and we're going to move towards a semicircle. So let's see what happens to the plot on the right. Okay, and this one's interesting because now you see the second breaking curve that's known to occur for NLS. And then by the time we get to this one, okay, we're getting closer to a semicircle, right? There's not too much setch left. We're starting to see a third breaking curve, okay? And now we're up to 1, 2, 3, 4, 5 breaking curves. Okay, but furthermore, what's happening is the you notice all those peaks, right? They seem to be coalescing. Right? Those peaks that were at the locations of the poles of the tritone K solution, until finally, okay, something seems very special about the semicircle. Okay, where now, first of all, you're getting, it seems to be a time periodic solution. Yes.
How long is n?
Right there.
Oh, okay.
Yep, 10. So you can also count it by doing 1, 2, 3, 4, 5. You can see it there. Okay. But anyway, so I love these. I love seeing the this is the motivation, right? Like Garrett was talking about. You do the numerics first, so you know what to prove, right? And then you have a guide. So this is our guide. Sorry, I can't hear you. What? The initial data is the semi-classical soliton ensemble associated to the semicircle, so it's the red curve. Yeah. But it should, the solution, at least at time equals 0, we can prove converges. Okay, and Bob will be talking actually more about this particular problem right here. For the red, it's an exact solution. Yeah. I can't do an exact solution for the blue. Okay, so we're gonna more question?
Convergence in which sense? You said convergence to semicircle, in which sense? No, it's the same, right?
As n goes to infinity.
N goes to infinity.
As n goes to infinity, I get convergence to the semicircle.
Yeah.
Okay. Okay, so what we're going to do now is we're going to zoom in on that point there. Or well, actually, we're going to look at the same picture in 3 dimensions. Okay, so let's look at the amplitude of the NLS solution. So we'll do the same thing again. Again, this is what the setch solution looks like. You can see these little bumps that show up in exactly the locations that are predicted by, well, of course, it's an asymptotic result, but vaguely in the locations that are predicted by Painleve-III. Okay, and then as we pan across to the semicircle, these poles, or they're not poles, they're actually locally asymptotically described as peregrine breathers, but they seem to be gathering, right? There's a gathering spot for them. Ooh, and then, so they all get together, again, they all climb on top of each other. So this is what we'd like to understand in greater detail. Now, just before we go on to universality, just some obvious notes about this thing. First of all, I hope you can see it clearly. There seems to be one very tall peak, right, which dominates everything around it. So the people use different definitions for a rogue wave, but 2.5 to 3 times as large as the surrounding area. Okay, this clearly satisfies any rogue wave definition. So it's clearly rogue wave behavior. This picture here, I see symmetry in both space and time. Okay, we'll relax that later, especially the space symmetry. And yeah, I don't know if you can see it on the screen, but there seems to be a kind of a quiescent region over here. You see some black. So there's this function has a certain form to it. Okay. Yes, Ken.
Is that a picture in which 10 is n, or in which it's been rescaled and that's the limiting profile? Solution actually is
I see a 10 there, so that tells me that n is 10. I have not rescaled anything yet. The peak gets larger. Yeah, and if you're going to study it, you got to scale it. Ooh, okay. That was exciting. Okay.
Saying the peak amplitude is equal to n, so then limits?
Yeah, there is no limit unless you scale. Yeah. So what you do when you study it is you take a sequence of these solutions and you divide by n.
So you're rescaling.
I'm rescaling the dependent variable as well. Yep. And we're going to have to rescale you see these little tiny numbers here too, right? So we're going to have to zoom in the x and t directions. And so I'll give you the exact scalings. Okay, so let's talk about universality. Okay, so here's that picture I just showed you. That's an exact solution. It came from okay, what I'll call semicircular initial data, the semi-classical Soliton approximation of a semicircle. Okay, this is another exact solution. This is a different problem. This is a high order NLS soliton. We'll talk more about that in detail, but you see the behavior out here is very different. Okay, you see some big oscillations, and those are some solitons that are coming in, and yet over here there's no wiggles there. Okay, there are no solitons. We're decaying to a constant as we go out in small time, right? But in the middle, we're getting what seems to be exactly the same looking function. Okay. And then here's another problem, also an NLS problem, and a different setup with NLS though. We're doing non-decaying boundary conditions now. We take a high order peregrine breather, which again, I'll talk about in more detail. But somehow the solution in the middle seems to be exactly the same. Okay. And so these are proven results now. We actually have, well, some of these results are mine and some are others, people's, but we'll go through this in detail. And there are more examples. Okay, and so here's the universality part. So what this function, this behavior, which I'm calling Painleve-III focusing, since 2017, we've seen it in Okay, so the first time it showed up, okay, that was the 2017, was a formal argument by Suleimanov looking at the dispersionless NLS equation, okay, like Paulo talked about. And he derived this function. And then let's see, in the order I put these in, the ones that are in magenta here are ones that will be covered in other talks in this conference. And so yesterday, Peter already talked about the Maxwell block equations in the sharp line limit. Okay, that was the function that he was talking about. And then Bob, tomorrow, I believe, will be talking more details about these Talanov pulses, okay, which have their own very rich and interesting story. Okay, and so today I want to run through some of them in more detail than others, 4 different places where this Painleve-III focusing has appeared. Okay, 3 of them are, let's see, 2 of them are proven, and at least one of these is work in progress. And one is just a numerical observation. Okay, so let's start with multiple pole NLS solitons. Okay, so here we've got our focusing NLS. I've taken out the dispersion parameter for now. I'm going to write down the lax pair. Okay, we're going to actually use the lax pair in some detail. Okay, and so in particular, this the solution of NLS is psi. The spectral variable is little lambda, and the solution of the lax pair is this matrix U. Okay, so to get our notation down. And of course, we've got our scattering data, we've got our reflection and corresponding to radiation, and poles corresponding to solitons, just like Gerard went through in much more detail. Okay. All right, so what we're interested in this problem is, so usually when you do NLS and you put down your poles, you just put down a simple pole. Okay, you have a residue, right? The residue conditions that were listed, they've been listed on a couple different talks recently. So Manuela had them, Gerard had them. You have a simple pole. But for NLS, it's been known since the very beginning of the inverse scattering method that you can have double poles, for example. Okay, and so Zakharov and Shabbat studied that by taking 2 simple poles and making them coalesce. And so remember, each simple pole corresponds to a single soliton. Okay, it might be a soliton going like this in a straight line that way, and another soliton going in a straight line the other way. Okay, but if you are careful with the limit, then you can get a special solution with a second order pole, and it looks different. Okay, these things are not traveling linearly anymore. They've got a logarithmic confinement to them. So this is the solution that we're starting with. Okay, this is a second order pole soliton. So again, very classical. And so of course, what we want to do, since I generally study asymptotic problems, I want to throw not just 2 of them together, but infinite of them together, right? Or at least 10, right? And so, yeah. Yeah. That one is, yeah, it's on the imaginary axis. Yep, because it's it's not traveling. Yep. So, but yeah, you can make it go that way if you want, yeah, or even that way. So then it becomes a bit of a technical challenge to figure out how to deal with these, 10th order poles or infinite order poles in the limit. And so I just want to give a little advertisement here for the Bilman-Miller robust IST that we use to study this problem. And so this is joint work with Deniz Bilman, this particular section A here. So let me, just spend a minute or two talking about the robust IST, a little bit of a diversion. Okay, and so this is a very clever method to analyze inverse scattering problems where you have unusual singularities. Okay, and so Gerhard was talking a lot about how, right, when you do the inverse scattering technique, you have to keep track of which class of data your solution is in, right, when you evolve. And you run into some problems with that when you pose initial data that has scattering data with, say, branch cuts, okay, or you've got like quarter root singularities, things like that. But it's really an inverse scattering problem. Okay, it's not a problem with the NLS equation. Okay, these are well-posed solutions. So, for example, the peregrine breather has exactly that type of problem with its scattering data. So you have to be very, very careful when you're doing regular inverse scattering, dealing with these problems. Kind of an ad hoc, work with each problem on an ad hoc basis. And so where do these poles arise from? Well, there were these strange singularities like quarter roots. Well, what happens is you build this matrix U that we saw, right, the solution of the lax pair. You build it out of these functions that are normalized at a certain point, okay, and usually infinity for this problem. And then you extend them in analytically, and eventually you run into analytic obstructions. And so what the idea behind the robust IST is, instead of just starting at infinity and extending in with taking a set of solutions that are nice at infinity and extending them in, let's start with the solutions that are nice at 0 and extend them out. Now, of course, eventually you're going to run into problems there too, so you have to do both. Okay, you start with one set that's nice at infinity, one set that's nice at 0, extend them both. They both are nice for a while, and eventually they have to hit each other. Okay, but when you've got two functions, you've got sectionally analytic functions in different part of the complex plane. This sounds very promising if you're a Riemann-Hilbert person, because now you've got a jump condition on a contour. And so they made great use of this to study the high-order peregrine breathers, and then Bilman and I used it to look at multiple pole solitons. Yeah, and robust IST is also going to, in theory, help with things like accumulating singularities, which do occur for NLS. Okay. Okay. Now this is the most equations I have for any slide. Let's see, what do we need? What do we really need here? The main point is that how are we going to actually build these, build the solutions of the this function U, right, that corresponds to a high order pole. Okay, how am I actually going to do that? I'm going to use Darboux transformations. So it's well known that if you use a Darboux transformation, you can take, say, the flat, the 0 solution of NLS, throw a Darboux transformation on it. What that does is inserts one pole, and then on the physical side, that corresponds to inserting one soliton. Okay. And so what I want to do is I want to throw in lots and lots of solitons, right? Except they've all got a pole at the same point. And so the game is basically, of course, the algebra is a little more complicated, but the basic idea is you start with your flat solution, the U that corresponds to the 0 solution of NLS, throw in a pole, and then we balayage that, we sweep the pole to the boundary of a circle. We get a Riemann-Hilbert jump there, and then you can do it again. Okay, so now there's no problem. You can do a Darboux transformation again, throw in another pole, sweep away that pole, and then we iterate this over and over again. Okay, and as long as you're doing the same Darboux transformation over and over again, you're going to get a nice jump on your boundary even after n steps. Okay. And so these are just some details on that. I think the main thing I want to point out is that I've got this psi sub psi to the E2n, or psi to the n, which is the solution to NLS after n steps of doing this Darboux transformation. Okay. They're ugly formulas. Yeah. Okay. So since you asked, anyway, yeah, it's all explicit, but it's forced by the problem. Okay. The other thing I wanted to say is that I've got and this will be important actually. I've got some parameters that I can throw into this. Okay, and so it's basically really one complex parameter, because if you, it's really in. This is really a point in a projective plane. So you divide out by one of them. But, okay, now here's what the solutions look like. These are again exact solutions. Up here on the top row is what happens if I choose my constants in that Darboux transformation to be the simple constants. Okay, and then everything is nice and symmetric, right? There's no asymmetry at all, okay? And this is, you've got 4, 8, 16 maybe that was 20, I forget, probably 16. So then at the bottom, we played around with this complex parameter, and you see there's still no velocity, right? Things are still just going straight up and down, but we've got some asymmetry. So since we're interested in this behavior at the origin, there seems to be some focusing at the origin that will change the non-generic focusing behavior. Participants can now see your, okay. All right, and those of you who are asking about the scaling, here is the space and time scaling. Okay, so I introduce a new time by n squared t, and I introduce a new space by nx, where n is the number of the degree of the pole. Okay. And this is to zoom in. The near field is to zoom in on this point. Okay. And far field is when notice I'm doing a different scaling in these pictures, right? 10, 20, 40, right? If I zoom out appropriately, then it stabilizes. Okay, but let's zoom in. That scaling that this near field scaling we just talked about. So again, we see this Suleimanov function here, as I call it, except it's now generalized. We've got a parameter that we can play with where it stays symmetric in time, but is no longer symmetric in space. Okay. Okay, so just to throw a little bit of Riemann-Hilbert analysis into this. So in all of these problems, how are we going to actually prove anything rigorously? Okay, we're going to have a Riemann-Hilbert problem. We're going to do Dive-Zhao on it. And then we're going to arrive at a model problem in an appropriate limit. Okay, and we're always going to arrive at this model problem. Okay, so this is kind of like the parametrics for that when you do this, when you get down to this point, you're going to see this Painleve-III type focusing. Okay, so for the Riemann-Hilbert aficionados, I think it's good to go through a couple of the details here. So in this particular problem, I'm fixing, okay, I've got x and t, those are my space and time, okay? So for the Riemann-Hilbert problem, you can think of them as parameters. Okay, beta, that's your velocity, Alex, okay? So that's the, where the pole is. This is I beta, no, I'm sorry. Beta is the, I'm setting all my, we actually have more complicated formulas I didn't want to write here that have an alpha, that's the velocity, and this beta is the imaginary part of the the pole. Okay. And then we've got these C1 and C2. They're just free constants that they can't be zero, but they're free constants that determine basically the skew, okay, whether you're symmetric or whether your solution's symmetric or not. So define some matrix S that only depends on the C's. And now we're looking for this 2x2 matrix A, which is a solution of the following model problem. It has a jump on the unit circle. Okay, so the jump is just a circle, very nice. And then the jump condition on the circle, fairly straightforward. It's you take this S matrix and you conjugate this diagonal matrix here that e to the 1 over lambda. Okay. And then we see this, there's a conjugation by a phase, so you can see the NLS phase there, right? Lambda x plus lambda squared t. Okay. And before we've had to scale, before we were using small lambda, and now we're using capital lambda because we did a scaling. And then we do a normalization. We pick the identity as lambda goes to infinity. And now I'm going to, okay, I do the standard NLS extraction, right? You take the 1, 2 entry of your matrix, you look at the 1 over lambda term, right? And then multiply by 2i, you get a solution of NLS out, okay? I'm going to call that capital psi, okay? And it depends on various things, including x and t. So for this particular problem, using rigorous Riemann-Hilbert analysis, we show that these multiple pole solitons are to leading order asymptotically described by this function capital psi. Okay, and now we can start to investigate the properties of this capital psi. I call it Suleimanov's function from his 2017 work. Okay, and here are some plots when C equals 1, 1, and then when I vary C, I get a bit of asymmetry to it. And what have we got in the different, so what's happening here, right? What I'm actually not plotting Suleimanov's function here. What I'm plotting is the solution to these high order poles, right? Where, well, okay, 2 isn't very high, but even then it's already kind of looking close. So I'm just doing 2 poles, 4 poles, 8 poles, and you're seeing the convergence to a certain function. Okay. All right, so a few details about this. Why do we call it Painleve-III focusing? Okay, so as we said, it was first studied by Suleimanov in 2017, and then Katayev did some work on it in 2018. So it satisfies NLS. We saw that from the Riemann-Hilbert derivation. Okay, and then there's some other interesting properties it has. These are, not surprising. You often get Painleve equations as reductions of NLS. So if you fix a time, okay, for any fixed time, then you get this equation, which you probably recognize as the second member of the Painleve-III hierarchy. Okay, there's actually a couple different Painleve-III hierarchies out there in the literature, and this one is by Saka. Turned out to be the one we needed. So anyway, it's a fairly complicated equation, but you can set t equal to 0, and then it becomes the Painleve-III equation. Okay, and I mean, I'll let you plug in t equals 0 yourself there. But it's actually a simple, a special form of Painleve-III where 2 of the parameters are equal to 0. Okay, here I'm using the Jimbo-Miwa parameterization of the constants. Okay, so this is actually a really nice function. It's got lots of nice properties, including at t equals 0 is a solution of Painleve-III. Okay, so that was my overview of my work with Deniz Bilman, where we showed this function showed up where you have high order pole solitons for NLS. I'd now like to go through more quickly through three other places where this function either has been proven or appears to show up. Okay, and so this chronologically, this work actually came before the work I just talked about. But so peregrine breathers. Okay, we mentioned peregrine breathers before. I'm sure most of you are well acquainted with them. They're special let's see, the next slide probably says something. Yeah. So the peregrine breathers are special solutions of NLS if you, okay, notice I've put a -1 here. So now I've got basically you have non-decaying boundary conditions. Okay, so basically you want absolute value of psi to tend to 1 as X gets large. Okay. Yep, there it is. And so here's a explicit form of the peregrine breather. Okay, well-known classical function. So we talked about them before with generic Painleve-III breaking. Remember, you had you took the poles of the tree truncate solution, and then let's go back. Why not? Yeah, so you took the poles of the tree truncate solution, okay, and put them down, and they form this nice little triangle pattern. But then what do you do at those poles? Well, you put in a little lump, okay, and for small dispersion, those little lumps look more and more like peregrine breathers. So anyway, that's just another application of peregrine breathers. Okay, so now let's look at the spectral theory for a peregrine breather. What do you get? You get a branch cut, and then you get a fractional power singularity at the branch points. Okay, and so this is a case where you have to be very careful with the inverse scattering, traditional inverse scattering approach, but the robust inverse scattering approach goes through much more smoothly. And so what you then do, okay, so you've got your peregrine breather, you basically take it, one way to think of it is you take its, the Riemann-Hilbert problem for a single peregrine breather, and then throw in additional growth at the band endpoints. Okay, so higher order, it's got kind of like adding poles at the branch points. And then you get other solutions, and they're called the higher order peregrine breathers. And they have very nice forms. I mean, you can plot them explicitly, but that's not really the point. The point is to study the n tends to infinity limit. Okay, and again here, these are plots from the Bilman-Ling-Miller paper. You see this Suleimanov function emerging from the mist. Okay, and again, these are unscaled. There's a height 8, right? Okay, and so yeah, this work was all done completely rigorously with error estimates and full Diderot Riemann-Hilbert nonlinear steepest descent. So. Okay, two other things. This one's pretty quick. I find this one kind of amusing. So going back, this is something we saw before. This is the same Satsuma-Yajima data we talked about earlier. So starting with a hyperbolic secant, right? But remember, hyperbolic secant is only a soliton if it's 1 times hyperbolic secant. But I can take like 5 times hyperbolic secant and still compute the scattering data for it. Or I can now because Satsuma and Yajima did that. And furthermore, if A is coupled to epsilon in a particular way, right? I take epsilon, epsilon is the dispersion parameter in NLS. If I take epsilon to be this A divided by a positive integer, then I get reflectionless data, okay? And now some more details I didn't tell you about before. Here's the location of the eigenvalues, okay? And this is well known. They're just evenly spaced, filling out a little interval. Okay, but what I want to focus in right now is the connection coefficients. Okay, it's known that oscillate between positive and negative. Okay, and so if you look at the Camvises, Miller, McLaughlin work, okay, that's one of the assumptions that they make on more general initial data, that you've got alternating reflection coefficients, because that's really that gives you really nice solutions. Okay, and so so for Klaus-Shaw data, you can prove that these connection coefficients for your semi-classical ensemble are going to be alternating. Okay, and so just for fun though, I'm going to not make them alternate, and this is what happens. Okay, this thing on the left pops up. Okay, so I just take the Satsuma-Yajima eigenvalues, and instead of doing -1 to the k, I just put in -1. Okay, I solved the Riemann-Hilbert problem exactly. I plot the solution, and Suleimanov pops up. Okay, there's no proofs here. Okay, this is just a numerical observation, but I mean, I'm pretty convinced it's the same thing. So, and over here on the right, you can see the time evolution. It starts to look kind of like one of those semicircles, right, that we were looking at before, the semicircle evolution. And then we have a breaking point. Anyway, this is well beyond my understanding, but you can see many different NLS dispersive phenomena happening over here. So what I'm interested in is mostly this time t equals 0 profile. All right, let's wrap it up with some ongoing work. And so some of this is work that will appear soon. Other is still in progress. So as we talked earlier, the scattering problems for nonlinear Schrodinger and especially focusing and Sine-Gordon in laboratory coordinates, right? So we had a discussion earlier yesterday about the distinction between laboratory and characteristic Sine-Gordon, right? So I'm going to do laboratory coordinates. Okay. So then there's a relationship between the scattering problems for Sine-Gordon and NLS. Okay, it's not quite as straightforward as the relationship for characteristic coordinates. Characteristic coordinates is actually characteristic coordinate Sine-Gordon is actually the one of the flows in the NLS hierarchy, but there is a relationship with the laboratory coordinates one. And so here I'm going to write the Sine-Gordon equation. Now, this is another very well-known, well-studied integrable system. And one thing that's very nice about it is it has more rich behavior than NLS in the sense that it has both two types of solitons, okay, for decaying initial data. It has both kinks and breathers, okay? And one of the, they correspond to different topological charge. So if you think of Sine-Gordon as an infinite line of pendula that are all coupled to the next one, then these kink solutions correspond to where the pendula wrap all the way around, okay? And breathers have no winding. So, okay, and so with Deniz Bilman and Rajinder Mavi at University of Cincinnati, we've looked at the higher order kinks and higher order breather problems for Sine-Gordon. There's some interesting new wrinkles that come up there. We again use the robust inverse scattering transformation, and we've computed the far field behavior. So these are what the plots look like. Solutions of Sine-Gordon we're looking at real valued solutions of Sine-Gordon. That's generally what's of interest physically. And so this is just the amplitude. And you see a lot of similarities, right, with the NLS type solutions. We've got this elliptic region here. We've got a quiescent region here. We've got a quiescent region plus an algebraic correction inside here. We've got sort of a constant region here. And then everything seems to be focusing, right? All the solitons get together and first they form kind of a flat region. This really is a different type of region there. Okay, it's not just the numerics weren't resolved or something. And then this flat region collapses to a point. Okay, so many of the same characteristics. Of course, the details are different. Now, of course, sine Gordon, you're usually looking at an angle. And so it's not actually the solution of sine Gordon where you see this Suleimanov function, but it's the time derivative. Okay. And so if you plot the time derivative of these multiple pole kink solutions for various values of n, as n increases, we see convergence to a very familiar shape by now. Okay. So yeah, so proving that, we know how to, modulo the details, we know how to prove this, and that's ongoing work. I do want to finish up, this is the next to last slide, just by pointing out that the breather problem is actually a little more complicated. And so if you know about sine Gordon spectral theory, you know that kinks, right, the poles come in a complex conjugate pair, okay, but breathers, they come in a quartet. So it's a different problem. And depending on how you choose these constants C in our Darboux transformation, you can either get focusing here, where we'll expect to see Painleve-III type focusing, or you can get something else where it doesn't seem to focus at all. So anyway, just something fun for future consideration. All right, so let's wrap it up. So, and get to lunch. So the main point of my story is that it's been conjectured for a long time and established in particular cases that focusing in dispersive equations, depending on the equation, is described by specific Painleve functions. There's this like KdV type Painleve-I-II focusing, or NLS type Painleve-I Tritron K type focusing. Now, if you take the NLS focusing and you tune everything just right, you can get all these peregrine breathers to kind of all go to the same location. You suddenly get this rogue wave behavior that's described by this limiting function I call the Suleimanov function, and it is related to the Painleve-III equation. And I'm really, in the last few years, we've seen this come up in many different places. So examples include NLS equation, both with decaying and non-decaying data, and the sine Gordon equation. I think this really is going to be a universal type of behavior. So thank you very much.
Thank you, Robbie. Any questions?
I was just going to ask, so I didn't see, but probably you'll show me where I missed it, the robust inverse scattering transform for the multiple pole soliton solution. I mean, did you write down a Riemann-Hilbert problem for that, or just the limiting?
I did. I just wrote down the limiting problem. Yeah. So you do.
Is it the standard problem? The Riemann-Hilbert problem for the n?
Yeah. Yeah. No, I can kind of so how do you get a model problem? You kind of look at your Riemann-Hilbert problem and squint your eyes, right? So let's like unsquint. So if we look at the, where's that Riemann-Hilbert problem? Yeah, basically the problem is instead of this exponential term, you have a sort of Blaschke factor, okay? It's like a lambda minus pole divided by lambda plus pole raised to some power. And then you take a log, and when you kind of look at it like, think about it like a Riemann sum, it in a large n limit, it becomes that thing. So I can show it to you in the paper. Yeah.
Okay. The reason I'm asking is I don't see why you need the robust IST to write down that Riemann-Hilbert problem.
So people have done it's really delicate because you got to take two, you don't need it. I'm not arguing that. Okay, but it does make your life easier. You have to be really careful when you tune the two. You start with two separate poles and you bring them together, but you can't just do it just any old way. You got to be careful with the connection coefficient, or else you get a zero solution.
You don't need to take it as you can just formulate the problem with a higher order pole, right? That's probably what they're saying. Yeah, you should just start from a higher order pole in the Riemann problem.
Right, but then how do you get to a jump that you can analyze asymptotically? I don't know how to blow that out unless I do it step by step. Yeah, if I do them one at a time, I can blow it out. Yeah, I know I can pose the Riemann-Hilbert problem, but I can't analyze it asymptotically. Yeah. Okay.
Sorry, thank you. Thank you. I would like to ask you, so you get an ODE for the limiting solution. Yeah. Can you get an ODE in between?
Can I get an ODE in between?
Can you write? There is an ODE in between. Can you write it? Or?
You mean the ODE for the, like before we do the model problem? Is that what you mean? Like Ken was asking about?
Yeah, yeah. So I mean, yes.
Before. Well, it's going to be more complicated. I haven't seen that calculation done or done it myself.
Mm-hmm.
Yeah.
And maybe since I'm here, can you go to page 7?
Yeah, page 7. It's one of my favorite. Okay.
Can you be precise in citation of the first result? There are 3 authors in that result. Mm-hmm.
I'm sorry, what?
When you mention the first result, there are 3 authors, not only Dubrovin. Can you be precise the next time you make your slides?
Sure. Okay. Which other 2 are you?
Myself and Klein.
Oh, there's a paper. That's right. There's a paper with you and.
Yeah, the paper you mentioned is Dubrovin, Grava, Klein.
Right. Yeah, I agree.
Thank you.
You have a question, Bob?
Yeah, but I can just speak up.
Just for the people on Zoom.
So, Robbie, my question was, you said if you pick C1 and C2 not symmetric, it makes it breaks space symmetry. Yeah. Is there a way to see that it can only break space and not time symmetry?
Yes. I think you can read that off of the Riemann-Hilbert problem. I mean, are there other Darboux transformations that you could do? Like all of the Darboux transformations we do have a time symmetry to them. Now, of course, as soon there's a Galilean invariance, right? So you can always throw in a time, a drift, and then you don't purely have a time shift, but that's kind of cheating. So I remember, we really are just doing a particular Darboux transformation, like one that works out nicely. You could do all sorts of things. Now, this isn't going to change your time. You could throw in like Darboux transformation with like C1, C2, equal to something, and then do another C1, C2, and then go back and forth or something. I mean, the possibilities are really, you just have to choose something,
There is a characterized which solution of this kind of you get. We've got various characterizations of it. It's specified by its derivative at 0. That's one of my favorites. That's known. Yeah. So if I remember correctly, in the far field region.
Yeah.
At least for either, I don't remember if it was for the multiple pole or the higher order rock waves.
Yeah.
There's a central wedge in which the solution is a modulated elliptic wave that looks like the one that comes out of modulational instability. Is that the same for both kinds? Both. So yeah, if you look in the far field, it looks like the peaks, and especially if you zoom out, the peaks straighten up. And so that looks like a modulated elliptic wave.
Yeah,
I remember
it is, yeah.
in both cases, both for the higher order poles, for both for the multiple poles and for the rogue wave solutions.
You mean the peregrine breathers? No, the peregrine breathers, it's sort of this flat region here kind of extends forever. You don't get this.
No, I'm talking about the far field.
Yeah, I know, in the far field region, right? So as I'm like starting here, I've got Suleimanov, it's always the same, and then I move out. In this case, I move through a flat region, and then the flat region kind of breaks up. Well, it's not really flat, it's smooth. For sine Gordon, it's actually flat. For NLS, it's a nice kind of, arc shape. But then this smooth region, for the peregrine breathers just kind of continues forever to infinity, whereas for this one, you get this rapid oscillation. And you can do that for peregrine because this is a shelf, right? Or it's got some height to it. So eventually it'll connect to infinity.
Have you also done this asymptotics in the far field region for these?
Yes. Yeah, that's work with Deniz Bilman and Denshang Wang from Beijing Normal. Yeah. Yeah, that's published.
Okay, let's thank Robbie again.
Thank you.
And so we have a lunch break until 2:30. A quick announcement. Thursday, we're going to have a poster session at 4:30 for about an hour. So we have some people with posters. So that's on Thursday. But we'll resume today at 2:30.